We're looking at the directional derivative, weren't we? So we're finding the derivative of xy plus 2xz minus y squared plus z squared at the point 1, negative 2, 1 located on the curve t minus 3, and t squared in the direction of increasing z. So first, let's focus on finding the gradients. Still looking at the math. What is the gradient?
Y plus 2z, x minus 2y, 4z.
So y plus 2z, what did you say second one was?
X minus 2y,
And then you said
4z.
Does everyone agree? Re-examine your third component.
Oh, 2x plus 2z.
Go. And now we evaluate that at our point, right? 1, negative 2, negative 2 plus 2. 1 minus negative 4, 2 plus 2. And so there's the value of our gradient at the point. So let's do this. trying to find curve. Trying to plot 3D. Curve was t minus 3. Find a new variable point. Point was 1, -2. Why does it not look that? Oh, I think that's the graphics. Yeah, that's better. That looks pretty good. Okay. Right, so this is the curve that our point's being located on. And we're now, so say particles just like traveling, now we're at this point. We want to find direction of maximum, or we want to find a directional derivative, right? So, and in this case, we want direction of increasing z. Well, we only have two real directions from here if we're traveling along this curve. The tangential directions, right? So let's find a direction vector to the tangent line at that point. So really what we're looking for would be unit tangent vector, right? At that point. R prime of t. What was it?
0, -3, 2t.
I agree with the 2t. Why do you get 0 for the first component?
Oh, this should be 1.
And second component.
-2.
How do you get -2 for the second component?
It's like 1 - 3.
What's the derivative of 3?
It's
So that should just be 1, right? And then, yes, 2t, I agree. R prime of 1. Oh. First off, I already kind of gave it away. It's R prime of 1. So let me ask you this. How did I get t to be 1? And we want to find unit tangent at the point. So how did I determine t was 1?
Yeah, because of the X and Y component.
You said,
X and Y component as well.
of what?
Of the R prime, the R derivative.
So you're right to look at the components, but you're looking at the wrong one. And so remember, we're moving along a curve, right? What's the curve? R of t, right? What's the x component of R of t? T. Right? T squared is the z component. It doesn't matter, you can look at any of them. T, right? What's the x coordinate of our point? If the point's on the curve, t would have to be 1. Then just verify. What's 1 minus 3? Is that our y coordinate? What's 1 squared? Is that our z? So t has to be 1. Right, so t, the 1 is the parameter for that point. That's 1, 1, 2, right? Is z increasing? Why?
Because R vector R at 1 is 1 and R prime is 2. That's increasing.
So you're comparing R and R prime.
Yeah.
If you wanted to look if it's increasing, you want to compare R of 1 to like R of 2, right? And say, oh, that's obviously increasing. So just looking at the derivative, you can tell that z is increasing in the end, and the question is why. What is R prime? Derivative. What's the derivative?
Rate of change.
Rate of change. R prime at 1, the z component is what? Is that positive or negative? What does a positive derivative mean? So that would mean z is increasing, right? Specifically, it's increasing at a rate of 2 per step. So that is the correct direction. If it wasn't that, let's say that was negative 2, you would just do negative R of t, right? Or negative R prime of t, right? To flip the direction. Then you have your decreasing. But remember, we want a direction vector, not t prime, sorry. Which means we want it to be unit, so we're actually looking for the unit tangent vector t. Remember how to find t? What is it?
Derivative of r over magnitude or something?
Over magnitude of what?
Of r?
Not of r.
R prime?
Yes. R prime over magnitude of r prime, right? Again, kind of, the method is kind of given away in the name of t. It's the unit tangent, so just normalize your tangent vector. What is the magnitude of r prime? And remember, 1 at 1, so what's the length of r prime of 1? Root 6. So 1 over root 6 times r prime of 1. And I don't need to worry about writing that 1 over root 6 inside. I'm going to be doing dot product, right? There is our direction vector. And I'll just call this here as the direction of interest. Gradient of f at the point dotted with your direction vector, which has to be unit. Zero, 5, plus 8 is 13, times 1 over root 6. And 13 over root 6 would be our directional derivative. Again, we need the gradient. What's the gradient?
2x negative 4y.
Evaluate that at our point. And just to make life easy, oops, negative 4.
Yeah.
One. Oh, that's nice. they already gave us the direction. But is that unit? So I have to make it unit, which is simple. Oh, look at that, that's root 6 again for the length, isn't it? Now, directional derivative would be that dot product. 2 over root 6 times the dot product. 2, oh, look at that. 2 minus 2, 0. We just get 4. 8 over root 6. So the function that we were just working with, you want to find the direction of maximum and minimum increase and the values of maximum and minimum rate of change. How do you determine the direction of maximum increase?
Just take the gradient.
It's the gradient at the point, right? Didn't we already do that? What was the gradient?
1 over
What was it?
2 negative 1.
And what is the maximum rate of change?
One over root 6 to 1 negative 1.
So look back to what we were doing on Tuesday. Properties of the gradient. Specifically property number 2. We make it really, we make it a pop quiz. Really evil. The magnitude of the gradient. Four, 16 is 20, 20 and 64 is 84. And then square root of 84. Two 21. How do I actually spell out minimum there? I don't know. What is the direction of minimum increase? It's just the complete opposite direction, right? What is the minimum rate of change? What is it? So it can't be the same thing because you get 2 root 21 again.
negative of the magnitude.
Just the negative of the magnitude. And again, maximum is when theta is 0, minimum is when theta is pi, 180 degrees. We now move into double integration. So remember what an integral is? Limit of a Riemann sum. Double integral is limit of a double Riemann sum. That's enough. Right, so for right now, we're specifically talking about a rectangular region. Right, so if you look, you have your function, right? Function here. This is the region that we're integrating over, so rectangular. The idea is the same as with single integration. You want to divide your surface into sub-rectangles. Volume is area times height. Right? So you find area of each subrectangle multiplied by height and sum them all up. And this approximation gets better as we let the number of subrectangles increase to infinity. Right, so this is kind of saying what we just did. Right, to find the area of each subrectangle, this is what you do. Delta x times delta y, that's fairly straightforward. The height is you pick an arbitrarily chosen point. F of that point is the height of that rectangle. Single Riemann sums were annoying enough to work with. Double Riemann sums are even worse. So we're not going to be working with double hand sums. Assume functions f and g are integrable over rectangular region R. Suppose that S and T are subregions of R, and assume that little m and big M are real numbers. Right. Integral of a sum is the sum of the integrals, so that's the same. Integral of the scalar multiple of the function is just the scalar multiple of the integral. Again, that's the same. If you can write your rectangle as the union of S and T, such that S intersected with T is the empty set. So if you can write your rectangle as the union of two non-overlapping rectangles, except the boundary, that doesn't count, then the integral over R of F is just the integral over S plus the integral over T. Right, that is the analog of the integral from A to C is the integral from A to B plus the integral B to C. Right, where B is some point between A and C. So you can divide your interval, you can divide your region. Comparison theorem, if f is greater than or equal to g for all x, y in your rectangle, then the integral of f is greater than or equal to the integral of g. And so again, that's just your comparison theorem except for two varied now. And it's the analog of a Calc 1 property. If little m is less than or equal to f, less than or equal to big M, so you have f being bounded below by little m and above by big M, then your integral of f is bounded below by little m times the area of your rectangle, and it's bounded above by big M times the area of your rectangle. Finally, in the case where you can factor f as a product of two functions, one strictly of x, call that g of x, and one strictly of y, call that h of y, Then over your rectangle, the integral of f, right, over the rectangle AB times CD. Integral of f would be the integral from a to b of g of x dx times the integral from c to d of h of y dy. That's very useful. You're writing as a product of now single variate integrals, which you know how to do from Cap 1. And we have the notion of iterated integrals now. And again, we're only considering rectangular domains. So assume A, B, C, and D are real numbers. Iterated integral for a function f of x, y over the region AB cross CD. It's one of two forms. Integral AB, integral CD of f of x, y, dy, dx. Right? This is iterated in the sense that it would just be the integral from A to B of the integral from C to D, f of x, y, dy, dx. Right? So you integrate first with respect to y, that would give you something. Then you integrate that with respect to x. Or you just switch it. Right? Either of these would be an iterated integral. This next guy. This is such a cool name. Try makes this my favorite theorem. Fubini. I wanted to name my firstborn Fubini. My wife was having none of it. Such a killjoy, man. Maybe we should try to go for another boy and force the name Fubini. Almost two is enough. So this is actually a weak version of Fubini's theorem, because this is going to be defined just for rectangular regions. Right, so suppose f of x, y, function of two variables, continuous over the rectangular region R, from which is defined as AB cross CB. Then the order in which you integrate doesn't matter, is what Fubini's theorem is saying for rectangular regions. So you can either do dy dx or dx dy. Oh. Well, that's very similar to what Claret said, right? Where the order in which you take the mixed partial doesn't matter. Well, now since we're dealing with integrating over a region instead of an interval, remember the end of Calc 1, area between two curves? Well, that's a region, right? If you look at the region between the curves, we can now do it as a double integral instead. Again, I'm focusing mostly on rectangle, but area of a region is just the double integral over that region dA, which makes dA your area differential. Right? Your single integral differential, you had dx, that was a length differential. Right, now we have dA, our area differential. There was also average value from single integrals, right? I think that's Calc 2. We have average value of a two-variate as well. Average value over the rectangular region R of the function f of xy is just simply 1 over the area of your rectangle. That should not be an equals over here. Times the double integral of the function over the region. Okay, so let's calculate some integrals. Starting with iterated. And so really what we're doing today and tomorrow is twofold. We're going to be looking at how to evaluate iterated integrals first, and then start working with integrating over a rectangular region. Being able to being able to evaluate an iterated integral is important because that's typically how we would evaluate a double integral. And as we're going to see, it is not the actual evaluation that makes multiple integration difficult. It is setting up your iterated integral that you need to evaluate. I'm not going to write this out every single time. What's going on? Don't fix it, yes. But remember, this is what we're doing. Integrate dy over x squared to x. So I'm going to use the shortcut and say, oh, well, integral of dy, that's just length of the interval. Which is x minus x squared. Well. Integral from 0 to 1 of x minus x squared. How did we evaluate integrals from Calc 1? What was the theorem called? What was the theorem used to evaluate integrals in Calc 1? Oh no. What was the most important result from calculus, from Calc 1? Fundamental theorem of calculus, which stated find the antiderivative, right, big F, and then it's f of b minus f of a.
I still don't get why that's the fundamental theorem.
Because it relates integrals to antiderivatives. It's what relates all of calculus. Just like fundamental theorem of algebra, you know what that is? Oh dear. Fundamental theorem of algebra, you have a polynomial of degree n. You have exactly n zeros of that polynomial if you account for multiplicities. Another way of wording it is every single polynomial can be factored into a product of linear factors in the complex plane. That's the fundamental theorem of algebra. What is the antiderivative of x? Fundamental. Antiderivative of x squared. A half minus a third. And there is your iterated integral, 1/6. So not difficult. Right? Just an iterated integral, so it's really just techniques of Calc 1 and Calc 2 done twice. First, integrate with respect to x. Antiderivative of x with respect to x. Antiderivative of y with respect to x. It's x times y. And x would go from y to 3y. No, we're late today. What is 3y squared? It's a quantity of 3y squared. Minus y squared is 8y squared over 2. So 4y squared. And then 3y plus y is 4y times y. Oh, that worked out nicely. Now we integrate with respect to y. What is our antiderivative? Two cubed. Something went wrong. That's because that wasn't supposed to be 3y plus y, it was supposed to be 3y minus y. That was supposed to be a 2, which makes this a 6, makes this a 2. 2 cubed, 8, 1 cubed, 1. What's 8 minus 1? Times 2, there's your integral. What do we have to integrate with respect to first? Oh, but wait a minute. There are no y's, right? That's going to make this a little bit easier. Because that's just being treated as a length now. And I don't need that. What's that? X squared minus x squared is 0. We're left with x plus 2. And then distribute that x through. Right? And once again, that is a simple Calc 1 integral. Two cubed is 8. Negative 1 cubed. Negative 1. 8 minus negative 1 is 9. 9 over 3 is 3. 2 squared is 4. Negative 1 squared is 1. 4 minus 1 is 3. 3 plus 3 is 6. And that would be that integral. Good. Any questions on what we did? Good. Start you off easy with multiple integrations. Lull you into a false sense of security. Like the homework on this double integral set is up. Won't be due until the Friday after spring break, though. We will continue this tomorrow.